This bit of research wasn't really intended to be research. It comes from a very selfish place, to be honest. We have a software company and we build different tools, and one of our main tools is a differentially private like SQL engine. But you always have a challenge where you really want to make sure that your implementation that you've built with your engineers does what it says on the tin. And so we had to obviously have a range of different types of tests and audits and stuff to convince ourselves and others of that. And so we built tools for these. And so this is really where this came from, trying to balance creating the least friction for developers through the development lifecycle while having pretty good assurances that you've built something that does what it says in the tin. So the idea is that differential privacy in theory sounds great, and often the promises that are made are based on a whole bunch of kind of theoretical assumptions that aren't always the case when you implement something in practice. So a very simple example of this, which we actually don't deal with, would be like floating point attacks. So if you just add, noise from NumPy random or something, you might be able to reverse that, looking at the lowest floating points. What we actually see a lot more in common is that people pre-process data in the first place and very often will branch based on private data, for example. Somehow through the code, they do something where they change the sensitivity, but they don't realize it. So the sensitivity that they provide to a mechanism isn't aligned with the true sensitivity of the data. And all of this can mean that what you report as your privacy guarantees aren't actually correct. And so there's ways to get around this that are pre-existing. And the first is the formal verification approach. And there are certain languages, like even if you go back as far as like Pink, etc., where if you code up every algorithm using a DSL, like a domain-specific language, specifically for differential privacy, you can get some pretty robust guarantees around it. The problem is that like you're never going to use this. I mean, it's so impractical to actually put into any sort of like product or solution. It usually requires having all of your data in memory and stuff. Like it just doesn't. It's just not practical, basically, for many like production systems. The second is black box auditing, and there's been a lot of advances in this. But even still, this typically relies on essentially taking a whole bunch of kind of like samples through a system and then trying to build up the distribution and work out what the empirical privacy guarantees are. And obviously for very high dimensional systems, you need to have a huge amount of samples, and often that's just not really scalable. And so that's a bit of a challenge. But the one that we use in software engineering all the time is we write unit tests, integration tests. We put them into our CI, and every time there's a release, something gets called and a whole bunch of tests run. And so we thought, wouldn't it be great if we could do something similar for our frameworks? And so that's what we did. So we tried to consider any piece of software that's applying differential privacy as really nesting the original data through some functions, through a mechanism, through some functions, through a mechanism, and so on. So this would form like a DAG, essentially. And when information goes through a mechanism and is no longer private, then of course you can use that any way you want upstream, but we're trying to analyze the full DAG end to end. So I think I can probably just explain this better than maybe it is on the slide. But the general approach that we took was that we noticed that in almost all of the frameworks, you kind of have two parts. So you have your mechanisms that you're applying. So this would be like make Gaussian or make Laplace or like, randomized response, whatever. It's going to be one of the mechanism steps. And they're usually sitting somewhere in some file or set of files within the code base. And then you have the original inputs. So you have the interface that the user uses where they provide the data. So maybe they provide a pointer to a database or like a pandas data frame or something like that. And we want to basically make sure that that data gets to those mechanisms with the correct parameterization, so passing through all the metadata correctly, such that we apply the mechanisms correctly in the first place. And this should be easy. This should sound very trivial. However, it turns out that it's not. So the general approach that we took was if we look where the original inputs are, so we can create synthetic data sets to run through a protocol. And if we wrap all of our mechanisms, then we can look at what data actually arrives into the mechanism. We can check the sensitivities across them, And we can replay that again for different databases that may change by a record, etc., to actually test the promise you're making to the end user. And so that's exactly what we do. So we call it record replay. So the first thing we do is in a unit test, we just literally run the flow, like, you provide some data and you run it through whatever your mechanism is. So this could be like MST or some SQL query or something like that. And just before it gets called into the mechanism, because we've patched the mechanism, so we've wrapped it, we're recording what the inputs are, what the sensitivity is, what the outputs are, etc. And then we run it again with a different data set. And just as it arrives at the point where it's about to hit the mechanism, we can compare what the inputs were, QD, between the two flows. And then we can take the output from the mechanism and we can replay that in the second flow. So now everything is deterministic, like we're not based on like random seeds and stuff affecting the mechanisms, but we can ensure the propagation of our sensitivities have been correct the whole way through the flow. We can also isolate the individual mechanisms, and we can do full audits on them, because now you're only looking at a single mechanism, so the dimensionality isn't a problem the same way as it is when you look at an entire system. So that's basically what we did. So there's different types of failures that you might want to check, like data-dependent control flows. So this would be like, you have an if statement and you're doing something different. If you have a value over 100, right, then you're going to clip it in a different way. So you might want to be able to identify that. Parameters, states, etc., etc. If the sensitivity is just incorrect. And so you would hope that we found all of the bugs in our code, but we also decided why not just test all of the open source differential privacy frameworks out there and just see how they stand up. Surely they're doing, they've been built by Meta and Google and SAS and stuff, so they should work well. But I'm going to skip through because I know we're tight on time. This is only showing you, it's all on GitHub, so you can try it if you want. But here, yeah. So of the 12 most widely used differential privacy frameworks out there, so this includes Smart Noise SDK, Smart Noise SQL, DPMM, Private PGM, which won the NIST prize, etc. SynthCity, Diffrib, etc. All but 4 of the 12 had catastrophic privacy failures. And so these were very often developed by the people who actually had developed the theory in the first place. And bugs were introduced because they themselves weren't unit testing and checking their mechanisms and the flow of their code. So if they're introducing bugs and they're coming up with the protocols in the first place, you're probably also introducing bugs, and that's okay. You should just test your own code. I think that's the take-home message we're trying to get across to people. Some simple examples, like Jam was a paper from a few years ago, maybe 2 years ago, and when they introduced it to PGM, they just changed one of the parameters from 2 to 4 somewhere along the line, which switches it from unbounded to a bounded DP, but everything else in the program was set up for the other, if that makes sense. So it was just like one number switch, but we could actually identify that through very, very lightweight tests. Yeah, in fact, the only groups who had frameworks that passed straight away was OpenDP, which is much more like a formal verification approach in the first place. It's very functional. And the mechanisms provided by Google, so Jack's Privacy and their frameworks. So the take-home message that I would strongly suggest is, if you're building differentially private systems and if you're releasing them to the wild, hopefully people use them and you have you contribute to the world because it's actually used by people. Please test your code. Thank you.